Well, this is where we left off last time. I'm just going to re-emphasize a couple of things. Like on the first box and the second box, we're going to be doing two very different things. And I want to make sure, like if you're getting confused by this, you're slow down. Stop working so hard. I'm saying A is a list. And what is it? 0, 1, 2. 0, 1, 2. And then on the next line, I say B equals A. And what does that mean? Well, remember, I copy over the contents of A. The contents of A is not the list. It's a reference to that list. So we get B like this. This is an example of an alias. A and B are both referencing the exact same thing. So I print out A and B, great. And then I say, okay, no, B, you equal 5, 6, 7. So here's what Python does. We go, okay, well, B is 5, 6, 7. So let's make the list 5, 6, 7. And then we say, okay, B, you equal that list. And of course, B doesn't store that list. It stores a reference to that list. We never changed anything about this list. So now A and B are two entirely, I mean, they're both references, but they're now not aliases. They're references to two entirely separate lists. Everything's fine. Any questions about what we just saw there? Now here, we're doing something entirely different. Here, let's go back. I'm never creating a second list. We say A is that list, B equals A. So we copy over the contents of A, which is that reference. And then I go and I say, okay, hey, B at index 1 become 99. So we go, okay, B, index 0, index 1, become 99. Now, because A and B are still aliases to the exact same list at this point, when I print out A and B, we see the exact same list twice. Why? Well, there's only one list, but we have two references to that list. Okay? I want to make sure the difference is clear. In one thing, we updated what B was referencing. Let me reword that better. In one thing, we updated what B was storing. It was storing a reference to a list, and we updated it to be a reference to another list. That was the first example. We updated B. In the second example, I went and I updated what B was actually referencing, that list. Okay? So the first one, it changed B entirely to something of the same type, a reference to a list, but it was an entirely different list. Where in the second example, like I just showed, I'm going and I'm updating the one single list that's there. The list that A and B both reference. Questions about that? If I see no questions, I'm going to assume this makes perfect sense to everybody. Awesome. That's great. Okay, yeah. Who do I have? A and B are referencing the same list. They're aliases. There's only one list, but we have two references to that one list. Regardless of the variables used to modify the single list, it's the list that's being altered. If you expect B equal to A to make a copy of the reference, well, you're wrong. Okay, warning. The idea of references as aliases is going to be happening a lot from now on. So this is important to understand. But if you feel like okay, I get it, but I want more experience with this, don't worry, we're going to get a lot. Okay? Because that's basically where we're going from now on. Is like almost everything's going to be a reference unless it's a primitive type. If you do want to make a copy of a list, well, lists have a built-in method called copy that return a copy of themselves. Or you can even just slice a list, because whenever you slice a list with syntax like this, it makes a copy anyways. Who wants to take a wild guess? Which of those two examples there do I prefer? Which one is what I would say is objectively the better one of the two?
The top one, because it's not Python either.
That's a very good answer. What were you going to say? So you put those two together, you've got the perfect answer. One, I mean, you're kind of saying the same thing, different ways. The top one is, what do we do in that list? We're copying it. Well, how do you know? Because it literally says copy. It's pretty damn clear. What's the bottom one doing? Well, if you're an experienced Python programmer, you go like, oh, that's making a copy. But if you're not an experienced Python programmer, let's say you've got 20 years experience in C++. You're a wizard, and you've never seen Python before. And if you've never seen Python before, but you see that top line of code, you're going to go like, oh, it's making a copy. If you've never seen that second line of code before, you're an experienced C++ programmer, you look at that second line, you're like, what the hell is that? What is that? That's some magic syntax I obviously don't understand. Well, the top one is, I may have never looked at a line of Python before in my life, but if I'm an experienced programmer, I look at that top one, I know what it's doing. It's making a copy because it says it is. So to me, I like the top one because it's more self-explanatory. It's more obvious what it's doing. And remember, I've said it once, I'm going to keep saying it. Computer code is for humans, not computers. Contrary to what you've been told, computer code is for humans. So make your code as descriptive as possible. All right. Yeah, let's do this activity real quick. It's for wet wipes only.
I don't know where else to put it.
You're right.
Wet?
Close enough. It's definitely not recycling. All right, here's an activity. Create a list L with an arbitrary contents. Now, really, what I'm saying is create a list to have it referenced by the variable L line. Then create an alias of L called L alias, and then create a copy of L called L copy. Of course, I'm being pretty rough with my terminology here, right? Make a copy of the thing that L references is perhaps a more correct way to say it, but I think you know what I mean. And then convince yourself that you did in fact make an alias and then make a copy by playing around with it. So I'll give you a moment to do this, just to try to make this sink in real good. If you need help getting started, there's an example of creating an alias and then a copy. But now, how can you convince yourself that you've got that? Raise your hand if you're done. Raise your hand if you'll be done in like 2 minutes. Cool. So here's how I convinced myself. Let's start by looking at alias. Well, on line 6, I say L alias at 0 become X, and then skip line 7 for now. And on line 9 and 10, I print out L and L alias. And we can see, even though I only, it might seem like on line 6, I only altered L alias. No, I altered the list that L alias references. And L alias both reference the exact same list. Then if we go to line 7, L copy at index 1 becomes Y. To be clear, the choice of X at index 0 and Y at index 1 is entirely arbitrary. So L copy at index 1 is Y. Well, I printed out L and L alias, and we can see that neither of those has a Y at index 1. Only the list referenced by L copy is altered. So in this example, how many lists are there? Don't shout out an answer. Take a moment, think about it, and then answer the question in your head. How many lists are there in this example? And then if that question is unclear, here's the follow-up question. How many references to lists are there? Those are two very different questions. How many lists are there, and how many references to lists are there? Raise your hand if you have an answer in your head. Don't worry, I'm not going to call on you. Just really high. Do you have an answer committed? Raise your hand if you're like, well, I kind of do, but I'm too nervous to commit. One person, half a person, two, okay. Let's work through this. On line 1, how many lists are there? Line 1 has been executed. Now we're waiting on line 2. The computer hasn't run line 2 yet. How many lists are there? 1. Why? It's right there. There's only 1. And how many references to lists are there? 1. L. Great. Line 2, nothing happens. Line 3. How many lists are there after line 3 has run? There's still only 1 list. But how many references are there to lists? 2. L and L copy. Nope. L and L alias. Oh, ooh, that's terrible. Ooh. Then finally on line 4, how many lists are there now? 2. L, well actually no, I'm wrong. The list referenced by L and L alias, and then a new list that happens to be a copy of L. So let me draw this. After line 1, I have this. L is, what did I say? A, B, C. Right? That's what I have. Line 2, nothing happens. Line 3, I go to L. I almost wrote copy again. and I copy the contents of L, which is not a list, it's a reference to a list. By the way, I keep emphasizing like L is not a list, it's a reference to a list. But almost everybody, including myself, will, as we carry on, will say things like L is a list, even though we all know it's not. Really, it's a reference to a list, but be aware that that's how we kind of word things. But L alias, there we go. So this is after we've run line 3. There's one list and 2 references to a list. And then finally, we run line 4, and we have L, copy. I'm trying to write fancy on an angle. Let's try that again. L, copy. And we make a whole copy of that list. I'm not going to write it, I'm too lazy. And we do that. I better write it to make it clear that it is, in fact, a copy. A, B, C. There. So this is the state of the world after line 4. How many lists are there? 2. How many references to lists are there? 3. 2 happen to be referencing the same list, but that's fine. There's no limit. I can make a bajillion references to one list. It doesn't matter. So any questions at this stage? So when I go along and I say, okay, L alias at index 0, well, L alias at index 0, that's this. We obliterate that, we turn it into an X. And then I say L copy at index 1, well, that's this B down here. We've got that. That's the state of the world. Can you see that reasonably well at the back? Yeah? Good stuff. Questions, thoughts, concerns, anything? This is very important to understand. Functions and aliasing. Okay. When a list is given to a function, the parameter, remember, in this example, L is not a list. L alias is not a list. L copy is not a list. They're all references to lists. So when I give a list to a function as an argument, I'm never actually giving a list to a function as an argument. I'm only ever giving it a reference to a list. So here is an example of code that a lot of people would say is god-awful, horrendous, evil, bad, terrible code. This right here is disgusting. And if you can't see it, you're lucky, because it's absolutely horrendous what you're seeing right here. And the reason it's terrible is because this function here has a big bad side effect. I want to be clear. I'm being dramatic. Having side effects in your code is not necessarily wrong, but not having side effects in your code is a damn better sign. When your code has side effects, you are creating a disaster ready to happen. When you have side effects in your code, you are going to make, and I know I haven't explained what side effects are fully yet, I'm about to, but you avoid side effects at all cost. Because when you have side effects, in spite of what you might think, you make your code so much more complicated, so much more error prone, and just a goddamn nightmare. Functions, to be pure, functions receive input and produce output, typically. Okay? Write a function to add 2 numbers together. The function has 2 parameters. that get values as from the arguments, and then it returns the sum. Okay? This function does not return anything, does it? I mean, we all know, yes, it technically returns none, but there's no return here. Yet, when I run this code, a list gets changed. If I draw this, we want a function to receive inputs and produce outputs. What's bad, a side effect would be your function receives inputs, or maybe not, and your function produces outputs, or maybe not, and oh, by the way, this list is different now. That's messed up. Let me be clear. Look, this function receives a reference to a list and a value. Add to list. So this is like append something to a list. And then some list, let me put it this way. Let me draw this. This function takes two inputs. One of the inputs is a reference to a list, not a list. So there's no list inside this function that it knows about. This list knows about some list. This function knows about, it has a reference to a list that exists somewhere else. And then it modifies it. I'm seeing a lot of people going like, you're thinking too hard. You're thinking too hard. You're thinking way too hard. This function changed the list that it got like as an argument, as it could get to via the arguments. It changed that list. Right? There's no return statement here. I'm not saving a value that add to list gives me back. If I run this code and I print out a list, I will get ABC99. Is at least that part clear? Let me convince you. ABC99. But this code has a side effect. Really, what I should do, and even if you're like, no, I really want this functionality. No, you don't. You do not. If you wrote your code in such a way that you need this functionality, you messed up somewhere. You're creating an issue for yourself. Really, what you should do is, let me be clear on how I would do this the correct way, and hopefully it'll become much more clear. Let me call this like bad. Good. Now, when I hit run, what? It's because I never called it. Yep, thank you. So, bad, this is what we get. Oh, thank God, this is better. We never, a list got screwed with. We messed up a list. Now, we're safe. If you really want to make that function alter the list, don't. Make a copy of that list, leave the original list alone. Don't have a side effect where your function's screwing with something somewhere else. Make a copy, alter the copy, return that copy. Leave the original one alone. Don't create side effects. Leave your data alone. This is much better. At this stage, I could yell at you all I want about how side effects are bad, and you won't truly get it until you screw yourself over one day with side effects. And you're going to do it several times, and you're going to think back, damn, Dr. Hughes, he was talking to me. Yeah. You're not truly going to get it until you've been in the thick of it to see why you like it this way. Raise your hand if you're like in computer science and you're getting a computer science degree. That's your plan. Awesome. So there's going to be you're going to get a job, and if you do this, everyone's going to make fun of you a lot, and they're going to make you feel terrible about yourself. Because how foolish of you to have side effects. You don't want side effects. And if you get a job where they don't care about side effects, run. Run away. You are screwed at that job. That is not a good place to work. That's just bad. Obviously, there are exceptions to the rule. Obviously. But if you show up to a place and they're like, yeah, whatever, you know, mutability, side effects, fine. You are inheriting a mess. Yeah. What if they pay well? They won't. They won't. They're not good enough to have that kind of money. If they're making those kind of mistakes, yeah. If it's unclear what the difference is, at the end of the day, there was no return. This function had no return. I know it returns none, whatever. It had no return, and it altered something somewhere else. Ultimately, the function should get data, leave that data alone. It can observe it, but it doesn't screw with it, and then it returns a value. That's a pure function. As soon as you have stuff like this, let me put it this way. How do you write an assert test for this function? Without magically knowing that you screwed around with the assert. Let me fix that. There is no not a list. How do you write an assert test for this? I mean, you can, but you really got to hack it to make it work. There's no there's no return value to check what it's doing. Your assert test would have to look something like this. Not bad, but that doesn't look like any of the assert tests we wrote so far, where we would always have well, whatever this returns, we check it. Well, there was nothing to return. There was nothing to check. Ugh. Ugh. Terrible. So any questions about that? So side effects and pure functions. I had to listen to the example of a function that has a side effect. The function modified the list that was passed by reference. The term side effect comes from the mathematical expectation of a function. A function maps some parameters to a value. If I give you the function f of x, y, z equals x plus y minus z, and ask you to evaluate f1, 2, 3, you don't expect the value of x and y and z to change. X, y, and z are just there. Imagine the result is 1, 2, 3 is 0, but x is now 14. What? That's ridiculous. That's absurd. Don't screw around with anything anywhere else in your code. Don't have side effects. We can write a different version of that function that has no side effects. Functions without side effects are called pure functions, and we like that. So I just showed you this example. All right, this is what you want. Leave the inputs alone. Other questions, thoughts, or comments, anything? All right. So now to just blitz some list trivia at you. Some of this you probably already know. You can get the length of a list in the same way you can get the length of a string. Just ask, hey, what's the length of this thing? We can have empty lists. You can have lists inside of lists, which is interesting, as you clearly saw in assignment 2. Although really you have lists that contain references to other lists, but you know. You can append to a list. That's a method. Now, you might say, my giant rant about side effects. And you might say, well, append kind of has a side effect, right? Like sum list. And we said sum list.append 99. Like we modified sum list. And you're absolutely right. But this is where we're dealing with a method. And it's modifying the thing itself, which is a little bit different. And it's because we're dealing with mutable data types, something that like we can change, which I know you can do with lists, you know, obviously. And usually it's things with lists, like your data structures. That's where people plug their nose and go like, look, with data structures, they're mutable. We access and change the data in the list all the time. But we're doing it very carefully through like methods, which we're going to learn a lot more about very soon. So I know it's like, well, hey, you just said side effects. I know, but it is different. And if you honestly don't see that it's different, just look harder. All right, we can concatenate lists with plus. You can do that. That's pretty cool. But notice that it makes a new list when you concatenate lists. It makes a new list. List A and list B are they're left alone. List C is a new list that is the concatenation of the two lists. You can multiply a list. And there are some built-in functions that will work with lists. Like you could say min, max, sum. You can ask the min of a list. It'll tell you the smallest number in that list. Max. Sum. You can sum up the values in the list. That's pretty cool. Now, think about this for a moment. Like Python, has the built-in function like min, max, and sum, right? Sum. If I said, hey, what's the sum of the list? Well, just add up all the contents in the list. It has a built-in function to do that. Awesome. But somebody wrote that function. And that's fine. You can use it. But if you think, there's just it magically knows the sum of the list. No. You call a function. The function has some functionality. And it gives you back a result. Someone had to write that. Do you think you're capable at this stage to have written that function if you had to? If Python calls you and says, hey, I need you to write a new function for the standard library called sum to sum up the contents of a list, could you do it? Yes, you could. You're damn right you could. You know how to do that. Sure, there might be some fancy Python crap going on in there. But in terms of the underlying functionality, how do you do it? You have like a variable to store like a running total, and you loop over the contents. And you add it to the running total. And when you're done, you return it. We can do that at this stage. If you're like, that's simple though. Well, yeah, but that's how we always write our code. Whenever you have a problem, you break that problem down into the simplest version of that problem, you solve it. And then once you have that solution, suddenly that more complex problems actually become a lot simpler because you have a function that does the other bit. And then you solve that one, and then you solve that one. So if at any point you're like, yeah, but that's a simple one, give yourself more credit. It's simple because the problem was framed as a simple problem, but in general, these are complex problems. So yeah, without using the built-in sum, write your own function, mySum, to add up the contents. Well, we just talked about it. But how different do you think that would be than the one in Python? Probably not that different in terms of the underlying functionality. You got to iterate over the contents and add it all together. If you had a length 10, how many times? Yes, here we go. So if you wrote that sum function, and if you had a list of length 10, how many things does your function need to add together? This isn't a trick question. This is that stupid of a question. 10. What if your list had 10,000 things in it? How many things would your function have to add up together? 10,000. Yeah. So that sum function is an example of a linear time algorithm. An algorithm that, if you double the input size, You double the amount of work. The amount of time that algorithm takes to run is proportional linearly to the size of the input. You double the input, you double the amount of work. You multiply the input size by a factor of 10, you made the total amount of work 10 times more. Cool? The key here is, and this is an interesting nuance that's important to understand. It's not so important for 161, but I'm giving you hints on where this degree is going. The key here is when we say linear time algorithm, it's not so much that, hey, I have 10,000 things in there, and I want to add up all the things. I have to put my finger on 10,000 things. Yeah, it's related to that, but it's more about how much work you have to do, how much the work scales as you scale the input size. Obviously, these two ideas are related, but there's a nuance there. So any questions there on that? Thoughts, concerns, comments, observations, points? Anything? Okie dokie. What do we got now? Tuples, dictionaries, and sets. So now I'm going to show you a few more data structures, some of which you're familiar with-ish in Python, some of which you're familiar with in probably just math, you know about it. And dictionaries are a weird one, but they're pretty damn cool and shockingly important. They're definitely underrated as far as computer science students, I would say, are concerned. Among software engineers, no, they're very well regarded. But computer science students tend to miss the point on how goddamn good they are. Not my students, though. My students get it. So addition to lists, well, there's a hell of a lot of data structures out there. But some very important ones that we'll talk about are tuples, dictionaries, and sets. They're not going to be, like, a list is a shockingly general purpose data structure that's used everywhere in like every language. It's fantastic. But it's, it's sufficiently complex under the hood. We're not going under the hood this semester. We will next semester. We open up that hood and we see, okay, how the hell does it do what it does? But yeah, lists are great. But other ones in Python are something like a tuple. You've seen tuples in assignment 1. And tuples are very much like lists. You define them with like brackets, except, not square brackets. We use the round parentheses. That's how you define a tuple. So we've seen this in several places. I showed you how it's a great way to like kind of package data together, quick and dirty. Python actually does it for you. Like, oh, my function can return 2 values. No, you just packed it all into a tuple really quickly without doing it because Python did it for you. And then you can unpack that tuple real quick. It's great. But we also saw it in assignment 1 with the latitude-longitude pairs. And what's neat about tuples is, well, okay, comparing them to lists, they're both ordered sequences of data. You can index a tuple. If I ask you, with that tuple, some tuple, and I say, okay, 10, what comes after 10? 11. Why? Well, it's right there. You've got an answer. There's like a nice linear orderness to it, right? If I had a tuple like this, and I say, okay, so first we have 5. What comes after 5? What comes after 8? What comes after 2? It almost feels like this, what are we, grade 2? Obviously. Yeah, there's an orderedness to it. And what's the orderedness? Well, it comes right after. I'll show you an example. There's another data structure that we'll talk about in like 162 called like a tree. Or how about a graph? And maybe this is like A, B, C, D. Maybe we have something called like a weighted graph. 9, 5. No, let's not have the weights. Okay? And if I say, okay, you're at, you know what? No, I don't want to use letters because that might sound like I'm giving it some arbitrary ordering. That doesn't really matter. Let's say I have happy face, a tree, an apple, and a what? A hamster? A fish. Because that's my fish. Deal with it. Right? So unlike the tuple, where I say, okay, what comes after 5? 8. What comes after the tree? The apple. That would make the least amount of sense in this particular example. What comes after the tree? An apple, apparently. I guess it kind of makes sense logically. You know what? Screw the apple. It's not an apple, it's a pumpkin. You know, Halloween, right? So what comes after the tree? You go, what do you mean? What comes after the color blue? Maybe, I don't know, it depends. So some things have an obvious ordering to them, and some things don't. So when I was like, what comes after 8? And you're like, oh, it's 2. It feels like I'm in grade 2. Well, yeah, but that's only because that one's obvious. Sometimes it's not. So these are linear collection. There's an orderness to it. You can index these things. I can say my tup at 2 is, 2. At 3 is 66. Like, I can do that. But tuples are very, 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 very limited in the functionality we have for them. In fact, tuples are immutable. You can't change anything about them. So if I were to say my tup at 3 equals x, not going to happen. You can't do it. They're immutable. And with that comes some niceness, whether you like it or not. I know you might think like, oh, but mutability gives me that extra flexibility. What if I want to change it? You don't. You might think you do, you don't. So like this is nice. We like it like this. Right? Tuples are great where they're great. Yeah, they're immutable. Once they're created, we can't change them. And they're ideal for when we need to pack some data together really nicely like this, right? Yeah. Any questions about tuples? Yeah.
Tuple kind of has a name that suggests it only holds 2 values. How big can we make it?
You go as big as you want. Tuple? No, that's you're thinking of a 2-tuple.
2-tuple?
Yeah, you could have a 3-tuple.
Okay.
Or a couple. But no, a tuple you could have as many as you want.
So what makes it different from the list?
They're immutable. You don't have a lot of built-in methods. Like if I go here, like right, so I can't change this. If this was a list, I could do that. It's a tuple, I can't. And then even then, I can be like my tup dot, well, that ain't gonna work. No, my God. Stop trying to be helpful. There we go. Like there's no, dot, there's count and index. I can't, there's really not a lot of functionality in there. So they're more lightweight, which is often a very good thing, right? Okay. Dictionaries. Dictionaries. I'm skipping dictionaries and we'll hit there tomorrow. And the reason I'm skipping is because I want to make sure we have enough time to talk about them. But sets. Sets. Raise your hand if you've ever heard the word set before. Raise your hand if you're pretty damn confident in the mathematical definition of a set. Okay, there is a difference. But quickly, a set is just a collection of things. But what's neat about a set is there's no actual ordering to the data in a set. A set is just a chunk of information. And if I say, what comes first? The answer is like, that's not a valid question. Now in Python, there kind of is an answer to that question, but mathematically, really, by definition, there isn't. So there is no ordering to the data. So there's no guarantee on the ordering of the data. And sets, unless we have what we call a multi-set, sets do not allow duplicates of data, which is pretty neat. If I try to add, well, I've got some examples. Let's say I have the set CSCI 161. I have Greg, Anna, Sally, Frank, and Frank. If I print it out, sorry, second Frank, you're not there anymore. We got Frank, Sally, Greg, Anna. That's what gets printed out. Why is the order different? Because there is no real ordering. The way I added that as a set, and look at the syntax, I wrap it in set. That's what I get. The ordering, that's what I get. Why? What happened to the second Frank? Not allowed. You're barred at the door, I guess. You couldn't get in. You can only have one copy of each piece of information. If I had Math 106, I could have like Frank, Ryan, Sally, Francis, Xavier, and Linda. If I print it out, there we go. That's what I get. I could even add something. I got Math 106, add Lynn. Great, I can add Lynn. Great. Where did Lynn go? Lynn didn't even go to the end, right? Because the order doesn't really matter. So I can create sets. And now you might think, but what's the point? This seems like a shitty version of a list. No, you're wrong. Because, first of all, now you could do this with lists. You could use the in operator with lists. But there's actually some magic happening under the hood with sets that makes this way faster, which we talk about with dictionaries. But I could say, is Ryan in 161? And it would say false. There's no Ryan in there. Are they in 106? Yeah, they are. So I can use this in operator. And when we saw this in operator, who here remember using this in operator on a list? We always kind of did it accidentally. We didn't really want to do it. And when we did that, if we had a list of 10 things and we had to do a linear search, how many things would we have to put our finger on to know if they're in there or not? 10. 10,000, how many things would we need to put our finger on to know if it's in there or not? 10,000. So with a set, if there's 10,000 things in that set, how many things do I have to put my finger on? 1. I only need to check one thing. You had it? You just knew, right? There was something about it. We're going to learn more about that, not right now, but it's magical. It does something called hashing. And we can use set operators really nicely. You might be familiar with some of these things. And by the way, if you're not familiar with the set operators, but you're familiar with the basic logical operators, you're going to realize it's the same shit, but presented differently. So this is an example of the union operator. Okay? You have information in one, information in the other. Sometimes they overlap. Like this is a Venn diagram, right? Sometimes they overlap. When you union two sets, you get everything from both sets. Okay? So, I hope I have an example. If I union 161 union math 106, I get all of them. If there was any duplicates, they're ignored, because I don't give a shit about duplicates. I get all of them in a new set. We also have something called the intersection. That's what exists. So union is what's from all sets. Intersection is what exists in both sets. So intersection allows me to answer the question very friggin' fast, based on the same reason that I don't need to do a linear search magically with a set. Intersection allows me to ask, hey, who's in both classes? Who's taking both classes? I can find out like that. Then we have set difference. Who's in one but not the other? Let's not worry about that. But like who's only taking 161? So who's in 161 but not in 106? That's what I want to know. What's neat though is for intersection and union, I could say A union B or B union A. I get the same answer. A intersect B, B intersect A, the order doesn't matter. Set difference, it does. Who's in one but not the other? Well, which one? Does anyone know the fancy math word to describe that phenomenon? That's a shame, because I can't remember.
Is there a possible function or fun if someone was like in one of the classes?
Yeah, you could just do in on both, I guess. Are you in this and in this? That's how I'd do it. So imagine if I asked you the question, this will be where we end on this. How many unique words are there in your favorite book? We'll load it up into a set and count the size of the set. There, done. Because it doesn't count duplicates. What would you do if I gave you another book and asked, which words do you have in common? Intersection. That's definitively what it is. Want to know the number of unique words that exist between the two books. Union, and then get the size of the union. Want to know which words in one book but not the other? That's the difference. Sets are great for what they're designed for. When you come to a place where you're like, damn, a set will be good here, probably will. Use it, have fun. But in general, it's pretty general, or it's not very general. Anyway, see you later. And don't let me forget that tomorrow we need to talk about dictionaries.